Alright, time for another draftphysics.com, debatephysics.com also, but so few. So unprepared and unqualified and ill-equipped, and they really can't make reasonable arguments. They can't do any, coherent reasoning. So the conflict between kinetic energy, 1/2 mv squared, the fable, okay, and the reality, which is momentum, where Professor Lewin says nature can deal with kinetic energy one way or another. That means it can destroy it, it can create it, it doesn't matter. But nature can't finagle momentum. You can't make it. You can't poof it into existence, and you can't poof it out of existence. You have to always account for it. It has to be conserved. And now this is an observation all the physicists, generally speaking, with very few exception, agreed. Okay, that energy is conserved. That it is something that just goes from place to place in the universe, and it doesn't stop being something. It doesn't ever get really used. It gets just converted into forms we don't like. Period. And then we can convert it back into forms we do like. But it's always just conserved, and momentum is the actual one that's conserved, and kinetic energy is nonsense. So the lever is the proof, frankly. It kind of just makes it clear. The law of the lever basically says, you can convert two mass going one velocity into a one mass going two velocity, and it's that simple. And those two things are equal. Applying a force on the other side, fulcrum here, let's say, just make the fulcrum a big sloppy line. These are the results you'll get. Same force will create these two effects. Now, it can't create them if you change the ratios of the relationships, so that's something to be discussed. But the idea is you can understand a wheel can be understood as just being another form of a lever, and I could make a wheel, and I could put a weight on the inside, a two mass, and I could put a one mass on the outside, and those two circumstances would be the same. So if I took the wheel and I spun it with the two mass here, I would do the same work, and I'd produce the same energy, and I'd have the same anything as if I put the one mass out here. So the one mass at two velocity is the same energy, force, impact. It's the same work to spin the wheel as it would be with either one of these relationships. And it's just an obvious kind of fact. Nobody should disagree, just as nobody should disagree that it does not take 25 times the fuel, okay, to spin something 5 times as fast. No, it takes 5 times the fuel. All right. So you can take this one step further and just say you could have made a device. Let's say a stick. Okay, so we have a lever, and we have one version, okay, of the stick. That we're going to put the one mass out here. Let's put it 4. A one mass out here, and we'll put a 4 mass in here. Okay, so it's 4 units of distance different. So we have a 4 mass and a 1 mass. And we could put a little whacking device here, so they're the same place. And the fact is, if we use a spring or some constant force, all right, to apply, and we get those two to be equal, that is, the lever moves the same speed, these two things are going to hit with the same force. Now, their theory says this is 4 times the impact power, with the one mass way out here. 4 times the capacity to bang, to hit, to apply a force. And, of course, it's not. They're exactly the same. The 4 mass here going 1 velocity is the same as the 1 mass going 4 velocity. Same thing. All right. So the point that people like Ian Gosling, they just don't want to pay any attention to how the thing actually works. So if they could, if they were willing to do all these experiments, you'd think they'd be willing to do them with just tiny variations. And one of the variations is to do your spring. So you hook a spring on, constant force, you put in a constant amount of energy, and you release it. And you see what the results would be. Well, take your 2 and put it here, and then put your 2 mass here, and then put your 2 mass here, and then put your 2 mass here. And what you will observe if you do that is that it goes fast in all of these locations. It'll go a pretty similar velocity. And the real difference is the weight of your lever. And so ideally, you put it the furthest out, it will go the highest, okay? Because your lever is going the slowest. And so you have to understand the mass of the lever is part of the work the spring has to do. The spring isn't moving just your 2 mass. It's moving the entire lever. So if you put your mass way out here, it'll get the highest velocity with the least movement of the lever. So the less the lever moves, the less energy you lost to moving the lever, and therefore the more energy goes into the object. So the idea is that yes, the further out you put it, the higher it goes a little less high the closer you get to the fulcrum, because the closer you get to the fulcrum, the faster you have to move the lever to get this object to go reasonably fast. So the faster the lever has to move, the more energy goes into the lever, the less energy goes into the object. So it will progressively go the furthest you put it out on the lever. Alright, so when you're going to compare a 1 mass to a 2 mass with this relationship, you have to recognize that you can't push one of them from the wrong position. That is, from a position where the lever has to move faster. You want to make sure that the lever is moving exactly the same speed for both objects, and that'll prove that it takes the same force for both objects to be pushed. They both took the same energy from the spring if the lever is using the same amount of energy. So if the lever moves identically, then you know the lever took exactly the same energy, and therefore you're going to see the difference between the 2 objects clean. So the first thing he has to do, if you're going to do this experiment, first thing you have to do is create a weight of the lever. That is, put any old weight on the other side. It doesn't matter what the weight on the other side is. And balance your weight. So if it's a 2 mass, and you just balance it. Just make sure it balances to the weight you have on the other side. And then, okay, take the 2 mass off and put the 1 mass over here. Now you'll make sure that the lever moves the same amount, because this distance will be perfect because the 2 balance to this same weight. So this same weight, they both balance to. That means the 1 mass is actually moving twice the velocity up and down. Okay, and the 2 mass, same velocity. So you have to make sure those are balanced. And then once you have established that, then you can put your spring on and do your experiment. Now, obviously, this weight is superfluous. It really doesn't serve any purpose. But it's good to have it just first to make sure you have these distances right. These distances have to be absolutely correct. A little bit off, okay, right? So if you put the 1 mass a little too far out, the lever moves at the wrong speed, and a little too further in, the lever is going to be moving at the wrong speed. So obviously too far in, the lever has to go faster to push it twice the velocity, which means the whole lever will consume more of the energy, which means it won't go twice as fast because the lever is using more of the energy. And if you put it too far out, the implications are less severe, frankly. You can't lose too much by putting it too far out, I don't think, because the lever moves less slow, and all you can do is add a little bit of energy to it, but it's not going to be much, because you're not going to change the speed of the lever enough, considering all the other liabilities, which is you run out of lever, frankly. Okay, so I mean the idea is to have this 2 mass at kind of the maximum position and the 1 mass at half that distance. I guess that would be the ideal. But the point is you have to make sure this 1 mass isn't in closer than it should be, because if this distance is closer than it should be, then this lever moves quicker, which means the entire lever moves quicker, which means the lever uses up more energy. So you can't do the experiment that way, and you can't do it the way he did it, which is balance the 2 mass to the 2 mass and then balance a 1 mass to a 1 mass. You have to balance both of them to the same mass on the other side. Then you know you have these distances right. So it's little stuff like that. These are all important variables. They don't care about important variables. They just don't care. And that's disappointing that people can be like that, but that's the way it is. And again, the other issue is shooting them up. It's well, I mean, I don't want to go into all the things. The problem is his drawing of a ruler is too far away from the actual objects, so he has a huge parallax problem where the camera is distorting what you're seeing. And the other problem is that the masses are obviously spinning, turning, flipping. So obviously all of their energy isn't going into linear motion. A lot of their energy, or some portion of their energy, is going into creating rotation, and that's a downside. So anyway, then you have the whole air resistance thing. They're not great shapes for flying through the air. Not ideal. Certainly, in some ways, not equal either. You could argue there's the twice as massive object isn't twice as, it has the same profile as the 1 mass, so they both have the same profile going into whatever the friction is. So obviously one of them's going to have an advantage in the sense that it's going to look like it isn't twice as big, because mass can be hidden in thickness rather than size. You can make you can make your sail out of a thick material and make it small, or you can make your sail out of a thin material and make it very big. And obviously one catches more wind. So I think that's enough. So just pointing out that they're arguing something that I think is impossible to reasonably defend. That is the law of the lever. Okay, it's kind of an established fact that levers conserve momentum. They can't make energy. And the fact is that energy is in the form of momentum for levers. It doesn't do anything with this kinetic energy thing. You can't make any sense out of it, because the 1 mass will weigh the same as the 2 mass if you put it 2 distances on the lever, which means it's going twice the velocity. And it's just a fact that twice the velocity for the 1 mass is the same energy, the same weight, the same force as the 1 mass moving, the 2 mass, moving 1 velocity. They're the same. One can't have more energy. All right, and then I could bring up the ballistic pendulum again. I could bring up hydraulic systems. I could bring up gears. Gears are basically levers again. It all comes down to that in some respects. But again, why are they defending something that just kind of can't be defended? The two theories are in conflict, and you have to choose one. You have to say, okay, momentum doesn't have to be conserved. The universe doesn't have to conserve momentum, or the universe does. You either choose kinetic energy as being energy or momentum as being energy, but you can't have both theories, because levers convert big M's and little V's into big V's and little M's. And that's what they do. And every time they do one of these conversions, you're going to end up with a momentum number and a kinetic energy number that are impossible to both conserve. You can't conserve both. One of them has to fail to be conserved. And it's just a fact. And I think it's obvious the one that's failed to be conserved is the kinetic energy. Just like in all the other experiments with, 5-ton trains, add 5 tons to the train, you get a 10-ton train going half the velocity, and you say half the energy's gone. Same momentum still, all the momentum's conserved, but half the energy disappeared. It's just nonsense. And it's sad that I have to argue nonsense. I mean, it's so trivially incoherent and silly, and on top of the fact that they have no evidence and that they have to do these experiments. They have to construct these experiments because in 350 years physics didn't bother doing any of these tests. They didn't do any of this. They didn't test any of this. They never even dropped 4 pounds 1 foot and 1 pound 4 feet and actually measured the impact force, with some kind of technically sufficient instruments. No such experiment. So I'm not arguing with people who are reasonable. That's the simple truth. A reasonable person says, yes, there's a real problem here with their physics. There's a real problem with these two conflicting definitions of what energy is. Momentum doesn't mean anything if you don't think it's energy. It's a useless term. It's a useless word. Of course, it's energy. And there are two competing definitions of the nature of energy in the universe, and they're obviously in conflict. They are not compatible. Anytime you convert energy from objects with different masses, you will have to destroy the kinetic energy. I mean, create it or destroy it. I mean, it's just hard to do the creation part because that's like the 10-ton train ejecting 5 tons. And, we don't have a practical way to do that without using energy, or what would seem like using energy. Anyway, so till next time and such, that's all. I can only do my part. I mean, I'll pause and I took some notes. I'll read them, but I'll see. But that'll happen. I was in the video, right? Yeah, you saw these drawings, right? Yeah, I guess I was going to the goodbye screen. Okay. Alright, tired. Rough couple of days. Nah, that does seem like all there is, so we'll move along. Blah, 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 blah. And such. So, till the next time, this has been draftphysics.com and debatephysics.com video presentation. Blah, 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 blah.